All right, so finally I got some camera working at least. So I think this one works. Yeah, there we go. So yeah, today we are going to do some prototyping together with the Raspberry Pi Pico and a breakout board that I've done since before. So we're gonna start off by connecting these two boards here together. It's gonna be a little bit boring to watch, but I'll try to make it interesting. So let me just bring chat to the right window. There we go. So yeah, I'm gonna bring up the Raspberry Pi Pico pinout, so we know which pins go where. So the idea is to map the GP0 up to GP16 and make them match what we want to do in the proper board. So just a small recap. All right, I guess people are still joining. But yeah, let's make a small recap. So yesterday I finished the PCB design for a Raspberry Pi Pico based flash card for the N64. Some people say it can't be done, so that made it interesting to me. So I really want to give it a try. So I did some quick routing. It still needs to be cleaned up, but all the nets are connected. And it will look like this. So we have the cartridge like this. And let me turn off the camera. Yeah, like this. So we have the cartridge, and we have a Raspberry Pi Pico based module that exposes all of the GPIOs. That is important because we need all of them. So on this board we have two SPI RAM chips, and the idea is to fill these with the ROM data and do quick access to. When there comes a request from the N64, we will fetch the data from the corresponding RAM and return the data. So I got a little bit impatient and wanted to actually code on this, write the code. So this board doesn't exist yet. I haven't ordered it yet, but I still want to work on it. So today we are going to connect a Raspberry Pi Pico like this. So the actual development board. We're going to connect this with flying wires to the breakout board that I made since before. So that's where we are. So now I'm going to have to map these pins to the corresponding place on the breakout board. So let me just show the breakout board on the screen as well. 1 second. Right, so let's do like this. So this is the breakout board. Yeah, so I guess I'll just get started. It won't be super interesting because I'm just connecting wires from A to B, basically. But at least, yeah, it has to be done. So let's get started. So basically, I need wires. Yeah, I need all of these wires. So I'm just gonna connect them. And sorry about the camera. I was really trying to get a nicer camera to work, but video for Linux, I don't know. It doesn't want to work. It's already struggling with the shitty webcam that I have. But yeah, it is what it is. So essentially, the idea is to have this board more or less, yeah, just hanging in the flying wires. It will be fine. So we need to map these to the corresponding signal here. So I'm looking for AD0, so it's pin 28. Pin 28, so the green one should go to 28. That is one. Okay. And then we have 29. Yeah, also sorry about the bad light here. It could be better. There's a Pi Pico module as a KiCad component, by the way. Oh, that's nice. That's nice. And also, welcome. Nice to see you here. I'm from Sweden. So I hope my accent is not too strong. But I might choose some weird words sometimes. Sorry about that. Okay. Yeah, I guess this will be a little bit boring, but it has to be done. So we have the brown is GP2. Okay. Okay, I think that is correct. So now it's time for 4 and 5. So that goes to the 36 and 37. So on the breakout board, I made these kind of very visible guides so that you can sort of, yeah, I don't know. I hope it helps me a little bit. Your accent sounds a little bit like German people. Yeah, I'm actually half German as well. But yeah, I'm born and raised here in Sweden. So, but it's kind of similar languages. There we go. Okay, so where was I? 4 and 5. Yep, seems too much. So now it's time for these two, 8 and 9. A little bit tricky to get to. Okay, 14 and 15 here. Yeah, I was out biking a lot today, so my voice is a little bit sore. Sorry about that. Was out for 4 hours. It was quite a ride. But it was fun. We had really nice weather today. Okay, there we go. So now this side is done. So now we need a few more on this side. So I'm just gonna make a connector here to make it easy for us to refer to how it's wired up. So connector generic, And yeah, let's just make it 25, maybe even 30, 32, or 29, I guess. So these are gonna be the Pico Gpio. So just to make it easy to refer to. So later on, I don't want to be confused as to which pin goes to where. So I'm just gonna see here, mark this one up. So we want so this is how it's supposed to be wired, and these are not pin numbers, but GPIO numbers. So this is GP1 and so on. It matches this. Oh no, it's off by 1 now. Damn it. That gets confusing. I guess I'm gonna just because later on we only care about the GP values. So let's see. Let's call this GPIO 0. Yeah. Now it makes sense. And I have connected up to GP15. So we're actually done with the whole bus. So the bus is fully connected now. Now we need the ALA L and H and the read and write signals. Thanks for the link. I'll have a look. Nice. That's really cool. Thanks again for the link. That was really helpful. Right, so let's connect the I guess the L, and then the H. So I'm not really sure which order we want to have these one. I guess L first. Yeah, jumper wires will work. It's fine. You know what? I'll show you a photo, and you might scream, but the truth is, it works. So this is the FPGA card that is currently on my desk, and this works. I've been playing Super Mario on it, so I know it's horrible. I know, but it works. But in this case, all of the wires are equal length, but the length shouldn't really matter. We're talking about tenths of nanoseconds, so that should be fine. I hope I didn't give you a shock. All right, then we need the read and write signals. I'm still not friends with the new KiCad. It behaves differently from old. Yeah, so I mean, it works. It's just horrible, but it actually works. So let's see here. Then we need the CSE declock and DIO. Declock. And DIO. And that's it. Like that. What just happened? Weird. Okay, there we go. Okay, so time to connect these guys. So 2 wires, 3 wires. So the bottom ones. Yeah, I'm not a big fan of connecting jumper wires like this. It's always, once you have a congestion, it's really annoying to connect. So let's see here. Damn it, I flipped them. I've seen FPGAs broken out with magnet wires, so it's hard to screen for anything. You're right, and I think I've seen that photo as well. It's awesome. It's amazing that it works, especially when you've read so much about signal integrity and, you know, that you have to be so careful about the signals and all of that. Like, everything matters, but yeah, sometimes it's good enough. Okay, so now it's time for the last 4 wires, and then we can actually start to code. That would be fun. So let me just connect these guys. Oh no. Okay, so these jumper wires were really, really bad. They just flew off. So I have to redo them. These are the 0 and 1. So they go to 0 and 1. Okay. Okay, now that is fixed. It's time for the last 4. So green is read. Okay. Okay, I think it's finally hooked up. I'm not gonna double check it. Or maybe I should. I don't know. Anyway, it is connected. It is beautiful. Time to write some software. Okay. So I guess I need to connect my debugger now. And then I can connect it to the N64 properly. And yeah. Oh, these are wrong gender. Okay, 1 second. I'm just gonna get some new wires. We need 5 wires. Okay, now the monstrosity is complete. So this is what we have. So I'm gonna connect this to my N64, connect the USB to my computer, and connect the J-Link to my computer, and we can start integrating the CIC chip to start with. Doing that, we will be able to see, yeah, if anything even starts. So yeah, let me just hook it up 1 second. Need some USB cables. Okay, I think everything is connected now. Okay, so I guess it's time to write some code. So I've never written a Raspberry Pi Pico software from scratch. So the question is, how do you actually do that? So we were looking a little bit at these examples yesterday. And we were able to build the Blinky and some other stuff. And we were able to flash it over the J-Link. So I'm just gonna do that now again. So I actually switched out my OpenOCD to the patched one, the fork. So I will be able to run OpenOCD just like this. So let's see if this works. Seems like it. Okay. Right. Okay, so now we're back at square one. We have hello world. We have a UART over USB, so we can debug, and we were able to program it without fiddling around using the JLink. So that's a good starting point. Still have the feeling that making protoboard Cradle for interfacing with the JLink and N64 breakout will be less hassle in the long run. Yeah, for sure. But in the long run, you know, we have this. So, and this, I will get these PCBs in like 2 weeks or so. Thanks for the follow. So yeah, for people joining just now, it's been a little bit slow because I was just connecting wires. But essentially, we did this yesterday, a PCB with the RP2040 connected to the N64 cartridge. And today we prototype using a Raspberry Pi Pico connected in the same way, but not with the RAM. So this will all be using internal RAM. So what I just done was to connect everything together with flying wires. And now I just verified that, yes, I'm able to program the Raspberry Pi Pico and I can run stuff and the UART is working, or the USB UART. So now we need to start writing our own software. So how do I actually do that? So I'm actually starting from square zero here. So I wonder, is it a good idea to try to understand these CMake thingies? Or can I like break out? Let's go to the hello world, hello USB. Like if I want to build this on my own, can I just do that? So let's try. So I guess let's start a new view in Pico Corp and open up VS Code here. So let's create a directory called software. And yeah, I guess we can just copy this here. So remember, I need to export the path in order to build. So I think, yeah, let me just put that in my environment. Hello, SariVolt, welcome. Okay, so now when I open a new console, this will be correctly set. So can I just do that? No. It will be pure C. And so currently I'm struggling a little bit because I'm completely new to the Raspberry Pi Pico ecosystem. So they use CMake and they have a SDK which works well with this setup. And to build the examples, you just run CMake in the root folder and it will find all of the other things. Hi, Bentmods. Ah, yeah, Gateware with NMyGen is on the interest list too. Yeah. So yeah, I've been doing a bunch of stuff with that previously. So just to go back a little bit in history, yeah, so I made a N64 cart using an FPGA, and that's written in MyGen, not NMyGen, but MyGen, because I'm using the LiteX ecosystem in order to get the soft CPU and all of that cool stuff and SDRAM working. So yeah, that's definitely on my interest list too. So yeah, question is, should I just go for Raspberry Pi Pico tutorial? Let's just accept that we are noobs. Let's start from 0. What is this? No. I just started trying to wrap my head around Latex and the DDR controller. It's a little daunting coming from pure Verilog. But anyways, I'm here to lurk and listen. Welcome. Yeah. So yeah, maybe I should just show you what I have, because why not? So this is the project ECP card 64. It's on GitHub as well. Should be able to find it. So it's all open source, and it contains everything you need. But yeah, basically I just hook up the, actually you're talking about DDR, which is a little bit of a different beast. But yeah, for the SDRAM, I'm just exposing the pins here, and then I'm using it by more or less just saying, I have SDRAM, please use it. Like so. Oh, it has an ICE40 as well. That's cool. I was thinking about going to MCH, to be honest, but I don't know. Too much stuff going on and the whole situation being uncertain and so on. But it seems everything is getting more and more cleared up. And actually, CCC is going to happen this year, and I'm so stoked. So for those who don't know, there is this CCC, Chaos Communication Congress, yearly hacker event, and where is the information? Anyway, they recently made a post that it will move to Hamburg and it will actually happen. Yeah, and I also got a hotel, and I really hope it's gonna work out. Of course, I don't have a ticket. I don't even know if I'm gonna get a voucher. Who knows? But I'm stoked. It's gonna be really cool, I hope. So yeah, see you there, Cybervolt. If you want, just ping me later on. It would be cool to talk. Yeah, so anyway, I built this FPGA project around the N64 stuff and so on. And I built sort of a mailbox over USB so that I can communicate with a program over USB, UART style. Or not really, but it's more of a mailbox. But it works, and it's fun. But we're not gonna do that today. So let's go back to the Raspberry Pi Pico stuff. Okay, yeah. And actually, yeah, someone else took this code and ported it to one of those cheap ECP5 boards that are LED controllers. Color light, yeah, color light. So that was really fun to see. Yeah, but anyway, let's try to learn more about Raspberry Pi Pico. How does it work? Blah, blah, blah. Okay, we need it. Like that, if anyone knows of a Raspberry Pi Pico bare bones example repository, please link it in the chat. So right now my brain is like, I don't want to learn, I just want to get it to work. Thank you. That's exactly what I'm looking for. Okay, so let's read this properly. Yep. So we already did this. And yeah, I have this in my environment. So oh, hey, look, I didn't realize it was you. Welcome. Hi. So yeah, I'm currently learning how to get started with the whole Raspberry Pi Pico programming. So okay. Okay, so here we just, okay, so I can basically just copy this whole thing and turn it into my own project. That's perfect. So let me just, oh. Okay, so it depends on the Pimoroni stuff. Oh, it's some C++ stuff. So I'm basically starting from zero. I don't know anything, and I'm just trying to get. So we've been building the examples, and we can run them. It works great. But now I want to create my own project, and I'm not really sure how to go about. You could go back to an older version of that repo. Oh, okay. So maybe this one. Yeah, this is cool, but I'm really bad at Rust. I'm trying to learn, but I'm really bad. Okay. I don't know. Maybe it's my stream brain that just doesn't work, but I'm not really sure how to get started. So we had this. Wait. I mean, Rust is cool. I really appreciate it, but I don't understand it. I've tried to learn, but it's difficult. So, oh. The thing I really appreciate with Rust is the compile time promises, more or less. The whole borrow checker and all of that. So you're more or less guaranteed that things, yeah, you remove certain bug classes and so on. Okay. So this is a little bit differently set up. So we have a bunch of applications. Okay, so it's like the example. Maybe I should just take the example setup and use that. I just want to get started. Yeah. Let's do exactly that. So what do we need from here? We need this. We need this. And then I guess one example. So let's take the hello world. And then we just remove everything except hello world. Yeah, thanks. Did I forget to copy? Maybe I'm just gonna do like this. Okay. Is there anything else we need from here? This one perhaps. Yeah, I'm a little bit confused. Oh, I messed up. I accidentally overwrote the source file. That explains everything. Okay, one more time. Okay, we're back on track. So now we can move stuff around a little bit. Cool. So let's start off with trying to implement the CSC chip, because that is we're gonna need that, and it's a good starting point, I think. Yeah, this looks better. So now we have just a handful of files, and wait, there's something missing. Okay. So let's import the CSC chip. So I think I'm gonna copy the one from the ECP cart because I'm most familiar with that. I already made some changes over there in order to detect when the reset pin is being asserted. So let's copy from here. Software. Yeah. So this all comes from this repository. It's open source, very nice C code implementation of the CSC chip based on reverse engineering of decapped CSC chips and all of that. Really cool stuff. So I made some changes to this already so that it survives resets of the N64. But yeah, I'm gonna need to adjust this slightly. So let's perhaps start with being able to read GPIOs. How do you even do that? So I guess I'll just use the examples and learn from them, because that's usually a decent idea with the SDK stuff and so on. So I don't really need IRQ. It's good enough with just having a while loop, because yeah, since the Pico has 2 cores, I'm gonna dedicate 1 core to be the CSE chip. So guess I'm gonna need these includes. And so what? Okay, now that works. Okay, cool. Okay, so you need to call. Maybe there is a. Okay. So we have 2 pins, and it's these 2 pins. Let's call it so we have these 2 pins, and clock is on GPIO 20, and the IO is on 21. Okay, so whenever you need to do output, you do the set dir. That's good to know. We're gonna need that later. So in order to write, we need to do this. Is N64 CSE separate from other bus and console workings like it was on NES? Yes, correct. It is a completely different. I think I can show it. I think it's this one. It's been nuked from the internet. Just want to show you the schematic, because schematic is it's always nice. But essentially, yeah, maybe it's not here for copyright reasons. But essentially, it's a completely different line. It's connected to the PIF chip, which is the Peripheral Interface chip, which handles your controller and the serial bus that is on the controller. And also, yeah, I have the PDFs and so on, but I maybe I just shouldn't show it on stream. I don't know. But I'm just gonna use Google. If it's on Google, I can show it, of course. Here we are. Yeah. That was not the highest resolution. Why don't I find it? Yeah, in any case, it is connected separately from the CPU, and or actually it's the reality coprocessor that is connected to the bus. But it's a funny architecture. I really want to show the schematic now. Yeah, okay, here we go. So this is, I think, someone else who replicated the schematic. So over here, we have the cartridge. And the cartridge is mostly connected to the reality coprocessor, which is this one. So this one is the magic, so to say, GPU. It's like the heart of the N64. It is connected to the RAM, and it's connected to the video and audio chips, and it's connected to the CPU. So this is the CPU. But the CPU is not connected directly to the cartridge. So whenever the CPU wants to access something, it will ask the reality coprocessor to fetch it, and then this one will fetch it from the bus. And yeah, you could either store it as a DMA thing to the RAM, and then later on the CPU can access the RAM through the reality coprocessor. So it's kind of a wonky architecture, but it's fun. But in short, that is how that works. But then you see these signals, they go to this chip, which is the PIF. This is the Peripheral Interface. This is where you have the different controllers connected. You see the P1, P2, P3, P4, and also some EEPROM stuff and some interrupt. But for us, the important signals are the CIC data and the CIC clock, which is, yeah, I don't know really which one it is. Maybe it's this one, data and clock. No, that one goes to the reality coprocessor. Yeah, so the security, as I understand it, is that this chip asks stuff from the CSC chip, and if it doesn't match, it will reset the system or change the clock or something like that. Or was it pin 1? Oh, yeah, you're right. Yeah. So anyway, there you have it. But it's kind of funny as well, because the CPU can, through the RCP, request stuff from the CSC chip. So the game Banjo-Kazooie 2, I think, is a little bit special because it uses some kind of challenge response and has a special CSC chip, which is, I think there's only like 2 games or something that uses that, but there the assets that are stored on the ROM are encrypted and can only be decrypted using challenge response from the special CSC chip. So pretty cool. Yeah, I guess it's the same thing as the NES, just slightly different. And the CSC chip, you should definitely check out the talk about this. It is really interesting. Let me think. Where do I find it? This one. So if you just search for this, check out that video. It's super interesting because it goes into really, really, really low level, as in decapping and yeah, all of that. Really interesting stuff. And the code that I'm using is a derivative from that research. So it's been ported to C code, which makes it easy to port, which is what we're doing now. So yeah. So I guess let's just do something very simple here. So I just want to read the pins. Yeah, let's just, how did I read it again? Gpio get, okay. I guess like this. Yeah, I am not that knowledgeable about how this, works, and like if user issues happen because of the security chip and so on, like legitimate boards not working because of the security chip are wonky and so on. But yeah, that's annoying for sure. But yeah, the Banjo-Kazooie game is partially, at least, encrypted using the challenge response, at least according to that research. And also, I think they fixed some emulator bug because some emulator had implemented this challenge response stuff, and they had probably sniffed the bus and mapped out all of the various challenges and responses you can get, but they had missed a few, and they were able to fix it because they had access to the actual chip level implementation. So really cool stuff. Okay, so this is how you read and write. Perfect. So I think, I don't know, I could just start implementing it instead. Let's just do that. So we need one more pin, and that is the, oh damn it, I didn't connect that. So there's the reset pin. Why don't I see it? This one, the cold reset pin. Oh, it's called cold reset. Okay, pin 20. Okay, so ideally we should hook this one up. Pin 29. Yeah, so just give me a second and I will try to do this. Yeah, 1 second. And that went to pin 20. Okay. How do I find 20? Yeah. All right, so now I've connected pin 20, cold reset, to Gpio 22. And this is actually a very convenient pin to have. Here. Because we can use it to check if the N64 has booted, which is a good first test that we can do. So let's add these here as well and start porting. So the only function we need to port is read bit and write bit. So when we're reading, I guess we need to. So the question is, which I don't really know the answer for yet. Can you have? No, you need to set it. Okay, so let's do that. Right. So I guess this makes sense. So whenever we want to write, we change it to output, and then we change it back to input again. That makes sense. So yeah, let's not do that here, and do that here instead. So in my previous case on the FPGA, I had like one CPU which did everything. So I could I needed to break out of the loop in order to do stuff. But we don't need that here. So we don't need to. Yeah, we don't need to do this stuff. All right. Okay, I think that should be it. Just realized that I forgot to solder a pull-up on the breakout board. So this might not work. Right, we need to call the function as well. Right, I'm gonna turn on the N64, so let's see what happens. All right, it detected the GPIO. That's cool. So it might actually work. We could add some more prints in the implementation to see what's going on. For example, like so. So this is gonna spam a lot if it works, but if it doesn't work, it's just gonna, I don't know, not print that much. Okay, so it doesn't work. And I believe this is because of the missing pull-up. Because I was a little bit stressed before the stream. I was just running around and soldering stuff. You see this pull-up? I didn't read about this pull-up being needed on the internet. Oh, wait a minute. Maybe the pull-up isn't needed. It's because of the code. Yeah, because I just realized when I was writing the integration here that the way we are driving high is by just doing just keeping it as an input. So let's actually fix that and drive it high if it's high, like so. Maybe this way we won't need the pull-up. It's different. It's different. But yeah, there should be a lot more going on. So I wonder what is wrong. What could be wrong here? So obviously this worked. Actually, no. Pull-up is needed. Data pin is driven open drain. Oh, hey Corgo. Nice to have you here. You can enable pull-up in microcontroller. Oh, thanks. I didn't even think about that. Okay. So okay. I like this SDK. It's so so nice. Let's just enable the pull-up on the DIO pin. Oops. And remove this ugly hack. that I just did. Okay. Oh, that was a pull down function for pins too. Yeah, I think so. Yeah. Yeah, you're right. It's common in FPGAs, I think, but maybe on microcontrollers it's not that common. So I wonder, why do I only see writing 5 and 11? Does that mean we don't get any input? Maybe I should move this. Make sure read bit function returns 0 or 1. Okay, good. It masks. Oh, wait a minute. Maybe. Non-zero for high. Okay. So it should actually be like so, I guess. Or let's just do it like this. Or maybe this is a problem too. Okay, that should be fine. Oh, thanks. I think that's a copy paste error. That's a copy paste error. Thank you. Yeah. That's a good spot. Oh, shit. You're right. Okay, here goes. Do you know if the printf function is like extremely blocking or something, that it affects timing. I guess so. But still, this looks kind of weird. We're writing 0, 1, 0, and that's it. So if we just go through the code. Okay, blocking for USB. Yeah, so I guess this is what we're doing. We're sending the hello, write nibble. Write nibble should write 4, I think. We can actually enable this print as well. So we are supposed to write, we're supposed to do 4 writes, but we are only printing 3 times. It's console region set. Yeah, I think so. Yeah, it's PAL. So it's a 1. So the third bit should be set. It's almost like we're missing 1 write. I don't know. Okay, so yeah, let's just build this and see how it behaves. Okay, so it gets stuck, probably because it's waiting for some clock stuff. So let's just remove these prints. They're probably messing up the timing. And then maybe we can add some more prints. Let's just... Let's just see how far it goes. Keep forgetting to turn off the N64 before flashing. Okay, so we get here. Okay, but maybe it actually works. Maybe it's just the prints that are stupid. So let's disable the prints and actually put a print here. So okay. So yeah, the prints were interfering too much. But now we have verified that we're actually entering the loop. So yeah, I think this is done. The CSE chip is done. Cool. So now we need to do something hard. We need to put this on a separate core. So is there some example that does multicore? Yes, there is. Hello, multicore. Really? Really? Is this everything? Really? This is amazing. Seriously, it's only 1 line of code. That is so cool. Can I just do like this? Okay, maybe it's crashing because I'm trying to print from the other core. No, because I don't have a... Oh. Let's just not do anything here. Oh, I think I broke it. I'm gonna restart my J-Link. Okay, it seems very sad right now. So I held down the button in order to boot into the bootloader instead. Yep, so that worked. So I guess because I didn't have the while loop, we ended up doing something funky, and I don't know. Yeah, I guess it's my command that is not proper for multi-core stuff. Because there were a couple of other configurations. Let's see here. Yeah, we have these two. So yeah, I guess I need to later on choose which one I want to debug. Let's see if this works. So I'm starting the N64 and I don't see the print. That is probably because the prints don't work from the other core. Maybe I need to call this one as well from the other core. Actually, I was speedrunning this too much, so I didn't really... Actually, they do print from both. Okay, let's just start with something very simple before doing our stuff. So let's just copy their code and do exactly the same thing. So now we're doing... Yeah, it is the same thing. All right, it's probably using the normal UART. To be honest, I'm not really sure why USB prints work at all, because I didn't really do anything special to enable it. I just go back a bit. Yeah. Strange. Okay, now it's stuck again. I guess we need a while loop. Oh, actually, when I pressed Control C, it sort of started working again. That was interesting. Okay, here we go. But the buffer is empty. All right. Let's just do some sleeping and printing. Okay, so that works. And let's print some stuff. Actually, let's... Okay, all right, we also need to stop it. Oh. Yeah, so this doesn't seem to work for some reason. I'm not sure why. Do I need to do this as well from this one? I don't think so. But oh. I only see the core 0 prints. Maybe I need to do something else as well in the config. No. That was strange. So I'm doing exactly the same thing. But core 1 never reports. Let's look at some more advanced stuff. Okay, let's try this example then. I'm just gonna copy the whole file because it's quicker. Strange, it doesn't open up a serial port. It seems to be in a lookup state. Oh, there we go. And it seems really nice, and I really want to get it to work. But why doesn't it work? This is the most simple thing. So I have two sleeps that are, yeah, they shouldn't conflict with each other. I don't see why this doesn't work. Let's do like this. Might be some weirdness with the USB STD out from core 1. I'd be surprised, but it's the only difference between your build and the example code. Okay, so let's not print from the second core and instead just pass messages. So yeah, let's do this instead. And then we want to do, actually this example doesn't print as well. So we don't need to do this fancy stuff. Let's just do like this. So we get something and then we return it with +1. Okay. So how do we do it? We need to something like this, right? So we're pushing 42 and we're popping it and printing it. So we're not printing from core 1. Okay, it's at least not crashing, but does this have a result? Yeah, it has. Okay. Okay, there's a void. Let's say we do like this instead. Okay, still 0. I'm not doing anything wrong here, right? Because I'm doing so few things here. Not much should go wrong. Init, print, start. Should I start the core earlier? Okay, still the same. Ah, what a shame. So should we try to understand what's going on here? We are enabling USB and disabling UART. Let's compare with this instead. Add executable. So let's just do like this. So this is the one from the example. Does the order matter? No, still doesn't work. And that's really too bad, because I was hoping to use this here. What more can we do? So actually, I mean, I don't need to pass any information between the cores. So I can actually start the CIC chip and just go on with my life. I could light up an LED from this core just to ensure that the GPIOs work, because it's really hard for me to verify if the CIC chip is working without the ROM loading working. So I'm just gonna add the GPIO for the LED, which I think was 25, if I'm not mistaken. Actually, let's look at some example. I think it was the Blinky, I guess. Yeah, let's just do this from here and turn it on. So if the LED turns on, we know that this core is actually running. Okay, so let's have a look. It doesn't light up. Let me light it up from the other core. Yeah, it lights up. So it lights up when I have it in the core 0, but if I have it here, it does not light up. So that kind of proves that core 1 does not start. Oh, because I'm not starting it. Let me just try one more time. Okay, I take it back. So the LED is lighting up. I just want to double confirm this. Okay, I have confirmed that the LED does light up. So, okay, that means that everything is actually working. So I don't know how we got here, why everything was weird. The message passing was still didn't work, but that doesn't matter. We can keep the other core running and just do whatever it wants to do. And we can focus on the cartridge on this core. Cool. Okay. So now we're back on track. I'm just gonna drink something. Okay, so now the actual fun begins. We yeah, it's time to implement the bus. So where do we even start? Where do we even start? We could try with a naive bit banging approach, just to get things started. Okay, so now it might be helpful to look at my old code where I implemented the cart in MyGen. So essentially, we have a state machine. A big, not that big, but a state machine that, yeah, has different states and it can go between them. And I think I should replicate this in C. So we get past this, the very slow init phase, where the bus is initialized, N64 boots up, and it reads these first words, and yeah, by doing this in C code, we can sort of just have a feeling that things are starting to work, and then obviously it's not going to be fast enough. That doesn't matter, because we're going to port it to PIO. But I think we shouldn't start with the PIO just yet, because we need a state machine first. So how do we write a good state machine? Maybe right. So I'm just going to move this over here, and we can compare the FPGA and C code. All right. Just gonna start some music for my own. Yeah, I'm sorry for not having any background music, but yeah, it's annoying to have to deal with the copyright stuff and so on. Okay, so which states do we have? We have init, we have start, we have, okay, we can actually copy this. Again, the idea here is to just have a starting point, normal C code, so that we know what we're doing. And it will not be fast enough, but it doesn't matter. But the point is to see that things are actually going forward, and yeah, maybe, hopefully I have not hooked up any wires wrong, but this will sort of confirm that things are sort of correct. Okay. So we're gonna need some Gpio mappings as well. Maybe I should just do this in a loop. So yeah, up to Gpio 22. Yeah, good enough. Okay. So we're checking that both of these signals are high. So we're in this state. So ALE-L and ALE-H are both high. Then we go to wait address high. Okay. And here we're waiting for the high part to go low. So I'm just going to do it like this. And then we go to the low state. And this checks if you're resetting the N64 while we are in the state machine. So yeah, this can also be refactored a lot, but let's just stay with this. Now the interesting stuff happens. Right, so we need to actually do some more stuff. So yeah, so at this point we should store 16 bits from the 80 pins. And how do we do this in a proper way? So I'm a little bit curious if there is a faster way to do Gpio get. With all of the bits at the same time. Oh, okay. Perfect. Thanks. So let's do that. So because we hooked it up the way we did, that 80 up to 15 is mapped to the same GPIOs. Makes it so that the GPIO value will actually match the bus value as well. So we don't need to move around bits. And where do we want to store this? So we can call this N64. So I guess let's do it like this. So first we get the high part of the address, and then we get the low part of the address. and then we combine it like so. Like this almost looks sequential, but it's FPGA, so it's all in gate wires, it's all constant. But yeah, now we can actually do like this. So we take the low part and we OR it with the high part, which is shifted 16 bits left. Makes sense, right? And at this point, I'm actually, you know, I could put a print here. So I think let's run this and see what happens. Oh. Been writing too much Python. Okay, I'm turning on. Not much happens. So let's put some more prints here. So I guess in each state change, we can put a print. Like so. Oh, okay. So it seems, wait. Have I made a typo somewhere? Right, because we're gonna, but this doesn't make sense. When the cold reset goes high, we go to the start. Let me try this one more time. Okay, so right now we are most likely here. We're waiting for the cold reset to go high. Just to double check this, I'm kind of gonna check here. Yeah, so the CIC chip is waiting for this one to become 1, yeah, which is the same thing that we're doing. Okay, so I'm gonna flip the switch and it just keeps spamming. So we're oscillating between these two states for some reason. So I guess it's this. Does make sense. Could be that the CIC or the PIP chip is not accepting the CIC chip for some reason, but I don't know. Yeah, so I removed this. So we're waiting for these two pins to become high, which is the same thing as here. And that doesn't happen. So could be that I have unfortunately wired something up incorrectly, or I don't know. Because this logic is more or less the same, I think. Maybe I should write like this, but it's essentially the same. Yeah, in it, I don't know. There's no missing break. Okay. I'm kind of out of ideas. I have probably connected something incorrectly. So I'm gonna double check the wiring. Logic analyzer scope would be very useful here. Yeah, you're right. And I have a SLI logic, which I can just hook up. The problem is, let me just connect the camera again. Oh, sorry for the bad light. But yeah, this is how it looks. Definitions are correct. Yeah. So at least, I mean, I have verified this in a separate project, so I know this is correct. I have connected it like this, but it's possible, of course, that I made a mistake when I connected the pins or wires. So I'm gonna double check that. But yeah, it's a pain, to be honest. You can hook up only early. Yeah, okay. That's good. That's good. Thanks. I will actually do that now. But 1 second. I'm connecting wires. It will take a little while. Yeah, I think it's a good start to write it in C so that we can see, things actually working, and then optimize it with the PIO, because otherwise we're probably gonna end up in some kind of debug hell where nothing works. So yeah, it's better to start here, I think. Could also be that I mixed up low and high or something like that. But we seem to be oscillating in the very initial states between start and init, and that's kind of worrisome. Yeah, connecting a little bit more. Whew. Okay, finally. Okay, some more USB help. Let's just try to get this sorted. Oh, there we go. There we go. Okay. Time to rename these. So I connected it like this. So this is 0, 1, 2, 3. So I'm gonna hook up these two wires as well so we can look at them. Okay. It's finally connected. Okay. So I guess I can just capture whatever. So let's just reflash it. Okay. One second. Okay, we're back. So Okay, we got some stuff, but it seems the USB became janky. I have it in a dedicated USB port. It should be fine. It could be this spamming USB thing that broke it. So let's try again. Okay, one more time. Okay, I guess I'm gonna lower the sample rate. 50. Okay, what do we actually see here? We see an oscillation on declock. So, Gorgo, if you're still here, if I don't remember incorrectly, this sort of means that the N64 rejects the CIC chip. Could that be the case? So actually, I'm going to remove all the prints from the CIC implementation, just so that we're sure that we don't have any yeah, so it's been cleaned. Okay, so now we have a clean capture. This doesn't look good, right? So again, maybe the, let's see here. When I initialize the GPIOs. Oh, right. I need to be careful here because I did this loop. But then again, I start the other core after this loop. First one is 64DD mode. Second is region. Third is low. And last is high. Right. But this is the declock. Right. So the N64 is driving the declock, right? It's so this the fact that we are seeing this in the logic analyzer means that the C64 is actually toggling the clock. So that is good, I guess. And then the DIO is pulled high because we set the GPIO to be a pull up. So the question is, why doesn't it go low anywhere? So let me just change in the code. So instead of doing this, we're just going to call this. We're not doing the multi-core stuff. So this is just to verify that maybe the multi-core stuff is interfering somehow. So let's try that. Oh. Okay, one more time. Okay, this looks different. And like you say, so 0, 1, 0. So this looks correct, right? First bit 64DD. Right, we are not 64DD mode. We are in region PAL. Third is low, fourth is high. So this looks correct. And then we do some other stuff. And then, yeah, here you can see the transfer, ALH and L and all of that good stuff. And here it's clocking out the, yeah, the stuff from the ROM. So this is what we want to see, but we don't see it because of the multi-core stuff. So if we do like this instead, and just do an infinite loop here, everything is exactly the same. The difference is that we are just running the code from the second core. Yeah, let's try that. N64 is off. We are capturing, turning on, turning off. And yeah, it doesn't look like that at all. So this, okay. Does it mean that we need to do this stuff from this one? I mean, we do this. I don't know. Oh, this really makes me sad. The multi-core stuff seems kind of broken. I don't know. I don't know what I'm doing wrong. We could try to turn off the USB stuff. So let's just turn off STDIO completely. Okay. And let's just remove the build directory. Do the CMake stuff again. And then flash it again. So again, just to show what we're doing. We are launching the CSE chip from core 1 and have a infinite loop on core 0. So capturing, turning on, turning off. And no, it is the same. So I don't know. I don't know. Something is fishy with the core 1 stuff. And that is very sad, because now we can't really do anything. So the question is now, how do we go about this? Should we go deeper and try to understand how to launch multi-core stuff without the library and like really understand it? I mean, this, yeah, it doesn't work. Can we just do a ping test on the chat? Like when I say ping, you say pong. Because there seems to be quite a delay. So let's just do it. Ping. Okay. Well, I guess we're gonna need to debug how this works. So let's go into the SDK and look at the implementation for this. Oh, and the chat is dead. Okay, there I got your message. Yeah, I mean, it is what it is. We are, how many are we? 11 people. It is what it is. But I'm happy you're here. It's been, it's always, I mean, honestly, it's enough if just one person is here, because it's always interesting. And you who are here, very nice of you to be here. So, okay, let's try to find the implementation. So, So where does the stack come from? That looks interesting. Okay. Yeah. Okay, I see. Yeah, so the question is there something wrong here? Stack one bottom. So I guess there's a LD file somewhere. Some linker script. Probably this one. And okay, stack one. Okay. So I guess this should work. Okay, so here we actually allocate the stack one. And we call it core one stack. Where is it used? Okay. I get it. Okay, but then this seems proper. So essentially we have two stacks, but if you don't start the second core, this will not be allocated. Seems okay. And what does this do? We initialize some stack pointer, entry, stack bottom, core one wrapper. What is that? It's a function. Okay. To be honest, I don't think I'm gonna get anywhere by looking at this code. I mean, we can, like I could see that the LED was lighting up, but I don't know. Can we just combine CIC and mem reading on single core? I mean, sort of ish. What we need to do then is to extend this loop. Oh, wrong project. So essentially, we need to hook in this while loop. So what we could do, yeah, for now, yeah, it's a good point. So let's move this to a function. Call handle CSE process. And that should not be a while loop. And then here, in the while loop, we process the CSE chip, and then we mess around with the state. And we do like this. Okay, let's just double check everything. Do this, we do this. And then immediately after we have our while loop, we redo the process. Then we also have the state thing where we do this stuff. Seems good. Let's try it. So N64 is off. Oh. Right. Okay. So recording. turning on and turning off. Okay, this looks good, but oh, wait a minute. There's nothing here. So something is, oh, okay. The time was just so much bigger. Okay, so this looks good again. So here we have the initial stuff, and then we have the seed stuff, I think. And then here we have the ALE, H, and L, and all of that. Good. So let's look at the prints. Nothing. That's concerning. Did I remove the prints? Did I remove the prints? No. Okay, this I do not understand. Because the cold reset is obviously, I mean, since the CIC chip uses that, we're blocking here, waiting for reset booting. CIC reading functions are blocking and waiting for yeah, I see. Damn it. So we can't do like this. Annoying. Okay, I don't, damn it. If only this worked. Should we try with a different approach? Like try the different launch variants? Because something is obviously not working with this, but I'm not sure what. So I guess I'm just going to revert this then. Just remove CIC process entirely. Yeah. Yeah, I mean, what can you do? Right. Ah, okay, I see what you get. Okay. So you mean like this. So that way we can see that the state machine actually does something. And let's try. Okay, the terminal seems broken. Oh, is it destated? Oh, here we go. One more time. Okay. Something is weird with my computer. I think I have too much USB stuff going on. Okay, turning on the N64. Let's wait a few seconds. Okay, that looks good. So now we should see this in the print, but oh, right, I forgot. Disabled this. Totally forgot about that. That explains everything. This is so messed up. Oh. Do you have USB UART? Yes, I do. The funny thing is, though, that would be like my 150th USB device on this computer. I have too much stuff. But yeah, it's a good point. I will, maybe that is better. So turning on the N64 and turning it off, pressing stop. And yeah, we can see this stuff here, which is good. But nothing here. Okay, so maybe I should do like this. CIC run should return after sending seed. Oh, oh, I forgot to remove this. That, okay, my mistake. Damn it. Okay, one more time. You know, let's have some prints. Let's keep these two prints so that we see when I press on the unit. That way we can see that stuff is actually sort of working. Or did I? I'm doing too much at the same time. Let's wait with this and do like this. Yeah. So we're still using USB now. And I found a mistake that I made before. And let's see what happens this time. Okay. Okay. That works. Oh, okay, we got the state loop. Which is weird. Or maybe that is the final state. Let me just try this one more time. Okay, it's only printing state to 1. So maybe I messed up somewhere else. So let's have a look at the Gpio mappings again. So with, let's hear this one here. So 16 should be L. It is. 17 is high. Read is 18. Write is 19. Okay, so that is correct. Did I do something wrong here then? So if both pins are high, that is what I'm doing here. And obviously that maybe this time window is too narrow. 20 microseconds. So we have a while loop. We switch on the state. We go here. We do this and we do that. And then we read this one. That should, I mean, 20 microseconds is a lot of time. So right now my thinking is that for some reason the Pico doesn't manage. No, oh, you know what? This is fishy. Because we keep. You know what? I'm gonna connect another wire to this one. If you're executing a printer from Flash, then it could take 20 microseconds. Okay, good point. So let's not print this one because it's really uninteresting. So let's try again with this small change. There we go. And let's record. On, off. Okay, we got the N64 booting print at least. But that comes from here. So we got this print. That could mess up timing as well, so let's remove that print as well. Try again. Turning on. Nothing. So that's weird. Please return after write it function. Okay, let's do that. Did I mistype? Oh, I'm stream brain. Oh shit, what am I doing? Turning on. Oh, look at this. Look at this. Check it out. This is cool. This is cool. So this is proof that the state machine works and we can actually do stuff. And awesome. Now the fun. So I guess, Corgo, is this when we have sort of a time window where we don't really have to conform, we don't have to respond to the PIF chip, like we will still get these signals. So just to confirm that, let me just run the trace again. So that we have like 1 second or something where we can actually test stuff. No, okay, look at this, we don't. But now it's completely broken again. I guess we get stuck in this state or something. Let's try again. Okay. Okay, so thanks a lot for that suggestion. So this means that we're actually entering this and we can clock out stuff, which means, oh, this looks bad. This looks bad. All right. Why do we get this address? That looks like a bit error somehow. I mean, I do have flying wires and so on, but we got 0, and this time we got C. That feels, almost feels like there's some stray stuff going on here. Could it be some that we're reading it too quickly? Like when we read this here, we should actually read it slightly later. Like in my case, in the FPGA case, I'm waiting for these two to go high. And then we go to this state. And here, once the H goes low, I am sampling the 80 bus, which is essentially what I'm doing here. And then I go to the next state. Oh, right, I'm printing the states. Fuck. Shouldn't do that. But yeah, let's keep this print for now. But this is good. Why isn't... Oh. I was thinking bits. Thanks. I was thinking bits. I don't know why. Yes. I don't know. I was thinking like, yes, F is 15. So I don't know. My brain didn't do the right thing. Thanks for the review. Okay, this doesn't look good. 44, 58, what the heck? I mean, it should be 0 in the beginning, right? So what the heck is going on? Did I really connect it so badly? Because in this case, right, I don't sample the bus. But okay. This still worries me. Oh, wait a minute. Wait a minute. I'm not thinking straight here. We are getting the GPIOs, which is 32-bit wide register, where bit 0 corresponds to GPIO 0, right? And we want GPIO 0 up to and including GPIO 15. So this should be correct. And then this part puts it together. And that also looks correct. I have the correct type. Yes, I do. So does this look like there's an electrical issue? Like it's my flying wires that makes it break? Yeah, and this also sort of 4460, and last time it was 4458. Or could it be that we're getting like a different? No, I don't. Look at the whole 32-bit value first without masking. Okay, good point. Good point. So just double checking. We read all GPIOs, we print them, we use them. Yeah. Okay. This looks fishy. Did I maybe mess up something in the init? So I think the GPIO init was supposed to set the pins as inputs. Pretty sure. Because there shouldn't be any pulls on this, right? I don't know. The fact that we're getting slightly different values each time, yeah. There will be a pull down by default. Okay, that's interesting. Okay. So let's try to turn them off and just see if there makes any difference. But still, we're getting high bits. Like the expected address here should be 0. Okay, getting something slightly different. I really can't explain this because this is how the waveform looks. So essentially, we're waiting for this moment to happen, where both L and H go high. So let's move this to the, let's move this away and move it here. So this moment is this. No, sorry, this. So both are high. Okay, that's here. We go to this state. We wait for H to go low. That's this one. And then that is right. That is when we sample. So unfortunately, I don't have any logic analyzer connected to the bus. That will be hell to connect. But I could connect, let's say, 2 bits to get an idea of what is actually going on. So for how long after the pulse is the address valid? Good point. Well, I believe this is accurate, and in that case, from this point until this point, it should be valid, and then it swaps really quickly. And then from this point until this point, no, actually from this point until this point, it will be valid. A flash cache miss is around 0.3 microsecond. Okay. You know what? Can I move this to a RAM function? Yes, exactly. Thanks. So let's do that. So let's call that function cart. And cart will do this. Oh, thanks. That's magic stuff that I didn't know. So just to confirm with you, is it enough to just do like this? That's a good point, Corgo. I could do that. Let's just try this run stuff, see if it works. Okay, different. It's different, but I still don't really understand where we get this. Try it again. But yeah, really good point about using the GPIOs for profiling basically. So let's do that. I'm gonna hook it up to the last GPIOs that are free. Okay, 68. Did I get 68? No, I got 60. Okay, so 1 second. I'm just gonna hook up these 2 pins. So let's call that. No, yeah, we know that. Just gonna double check some wiring. So yeah, it's gonna be a few seconds. Okay, it's connected. So let's just call this logic analyzer 1. And so that is GPIO 26 and 27. So let's just make sure we are initializing that. Like so. And okay, so where do we want to put those? Should we put them perhaps here? And then here perhaps? Or we could use it as a counter, I guess. So we have 4 bits or 2 bits. So this is state 0, 1. And this is state 1, 0. And then this is state 1, 1. Okay, let's go. Oh, I think this explains everything. So again, looking at the code, let's see here. Let me just fit everything on the screen. So state 01 is when we read L and H high. And apparently that happens here, which is probably from this. We're probably reading this, but did we miss this? It seems so. So it seems we are like way too slow. That is probably what's going on here. So thanks again for the suggestion about using the GPIOs for the logic analyzer. So this is proof that this takes place way too late. That should happen here. But it's actually happening, oops, all the way over here. So this is the first two reads, right? This is the this one, the 8037 and 1240. That of course we should respond with. So yeah, I don't know. Now the question is, why is this slow? Is it, to be honest, I don't even know if this code is optimized or not. Like I have no idea how this works. Where's the optimization flag? Where is it here? Maybe like so perhaps? Comment. Yeah, good point. Thank you. I will do that. Yeah. Of course. Yeah. I forgot about these. That's good point. So let's do another test. Let's record. And actually, let's. Okay. So, how did it go this time? Much better. Thanks again for the suggestion, JTH. Very good. So in this case, it seems to actually work. So this is the very first bus interaction, and we're able to catch it. And here we enter the 1-1 state. So I think this might actually work. Just wondering, do you still have USB STD? Yes, because I needed it for a little while. So let's change that back. So now we have everything disabled. Yeah, sorry. It's IQ driven and quite greedy. Okay, good. So just to confirm with you, if I do like this, I put both to 0, then that should not interfere with my code. So no IRQs and stuff. Because I'm not really sure, like the whole, USB init stuff. Yeah, okay, good. Let's give it another try. But yeah, this looks good. So this sort of, this looks good and promising, because we can actually measure, so the time from, okay, how do you actually, I don't use Sally logic that much, but I want to measure from this point to this point. From there to there. Can I do like, like I want to measure from this point in time to this point in time. A1. Okay. Yeah, here we go. A1, and then A2. How do I make another one? Okay, there we go. 60 nanoseconds. That is, yeah, it's something. That's actually pretty fast, I think, considering this is C code and we have a loop. With PIO, this will obviously be much faster, I think, because it will be running in the PIO stuff. So yeah, actually we could actually do this in the PIO with a logic analyzer output. That would be interesting. So that's cool. And then for the next state, which is from this point to this point, that is 100 nano. So I guess we were in a different state in the loop here, probably. But this is really interesting stuff. Or actually, is it? No, I'm measuring wrong. So let's do it again. So when both are active, that is when we enter the first 0, 1 state. Yes. So that is 160 nano. Okay. And then the second state change is when this happens and we enter the 1, 0 state. And that is 200. Okay, but even C code could go faster. That premature output. Yeah, correct. I think to be honest, we are at a point where we have confirmed that our C code does what we wanted to do. Let's not care about performance. So what we want to do now is to convert this state machine into PIO. And then later on, we will do the following states if possible and return data. So I'm kind of excited. This is cool. And thanks for all the help and finding typos and copy paste errors and so on. That's honestly really helpful. So yeah, okay, let's maybe I should commit this just as a safety. There we go. So let's have a look at a PIO example. So we had a look at that yesterday with some very, very simple thing. So maybe we should start with the CMake file to see if we need to do anything extra here. I think this is needed. Okay, that sounds good. Let's do that. So where should that be? Very early. Okay. So okay. So let's just start by copying this implementation and do just blink the LED, but from our code. So how does that work? So Okay, I can confirm that I see the LED blinking. So I've now imported the Blinky PIO into our project, and it works. So yeah, cool. Time to write some code. Yeah, high speed would be amazing, of course, but I guess there's a reason it's so unusual to see it in integrated, like the Phi integrated. I think there was one Chinese chip recently that got some buzz on Twitter that had integrated high speed, and it also had like Ethernet and stuff. If I'm not mistaken, I don't remember exactly, but I think there was some breakout board recently going around on Twitter with that chip. But yeah, having PIO would be, and high speed would be, yeah, really cool. But I guess, okay, I guess you could implement a, you know, connect to an external Phi with PIO, but I don't know. At that point, it gets a bit. Yeah, let me see if I can find it. I'm just gonna Google a little bit. 1 second. Oh shit. Is it the FX2? Or what are you using? Just gonna clean up a little bit in the open tabs. FX2 as cheap and more popular solution. Okay. Yeah, the FX3 seems to be quite the beast to work with. I ended up using an FTDI FT601, or actually FT600 in another FPGA board that I made a while ago. The reason was that I wanted, super speed to basically GPIOs, and the FT600 or 601 does that more or less. I'll show you if you don't know about it. So you have the USB 3 and you have a few GPIOs that you can set, but the important thing is the FIFO bus. And then in my case, I have an FPGA on the other side here. And then the FPGA can become anything. So I wrote some logic analyzer gateware, so I could sample pins super fast and feed it. The problem though, which is not trivial, is that latency is really messed up with USB, so you need memory. Otherwise it just doesn't work. So I ended up having lots of overruns until I realized that I needed a large FIFO. Because USB is USB. It's just, yeah, it is what it is. But it's a cool chip, but you need something on the other side. You can't just hook up like anything. You need to control, you need to speak the protocol. Yeah, I can't find that Chinese chip right now, but I asked a couple of friends about it, and maybe they will reply to me soon. Just get a huge hunk of, yeah, yeah, you're right. But yeah, I was getting started and just did some basic stuff, and I didn't really understand like that I needed that amount of RAM. But I basically used like tons of block RAM just for FIFO, which kind of sucks. So where were we? PIO. So okay. So what does this actually do? We call some init function, which I guess is generated because we have this .program stuff. And then we have this C code here. Right. So what does this do? Okay. It initializes the pin. This I don't understand what it is. Get default config. So I guess it's documentation time. We need to understand. Should I go to the SDK perhaps? So I have a little bit too many tabs open still. Let's clean up. Okay. So I wonder where was PIO explained the best? It was in the datasheet, right? It was a full chapter about it. So I have a basic understanding of the program, so I don't worry too much about the actual program. It's the rest of how things work that I don't really understand, like the whole boilerplate stuff. So okay, so these are some specific PIO. Right, I also need to initialize the GPIOs to become PIOs, right? Or I see. There is a chapter. Yes, okay. But I don't know, is my chat lagging so much? Or yeah, okay. Oh, it's the SDK. I see. Yeah, this is good. Yeah, okay, we can try ping pong again. Yes, I will say ping. And I will let you know when I see the response. Any second. Pong. Okay, there we go. So, need more warning. Okay, so I wonder what is the best way to actually get started here. So from we did some basic analysis yesterday of essentially what the program will need to do. But I guess initially we can just implement the state. I don't know, because we only have 32 instructions, but maybe that will be good enough to like this is basically can you wait for 2 GPIOs, or do you need to loop? I think there was some, wasn't there some instruction that could wait for a pin, but we need to wait for 2 pins at the same time. So but yeah, essentially, if we just think about what we want to do here, maybe it's easier if we look at the C code. So yeah, essentially we just need to wait for these GPIOs. So maybe this is only like one instruction per wait for GPIO. So I guess maybe we can just start by doing it simply and then expanding it later on. So yeah, this is where we initialize it. So we can start by renaming it. Let's call it cart. And just call it cart program init. Didn't quite understand what the SM means. So maybe that is explained here in the documentation. Right, there were 4 state machines per PIO block, and they could do the cool pin multiplexing thing. But I think in our case, we only need 1. Yeah, I think we only need 1. Because, yeah, we're just implementing 1 cart, not multiple carts. What does the offset do? Get default config offset. So in this case, they have some offset. Okay, so here it runs multiple state machines with 1 program. Right. Okay, so here it does that fancy cool stuff where you have 1 program but multiple state machines, and that's why you can have multiple LEDs blinking. The offset is wherever your program was loaded. Okay. Oh, I mixed up. Right. Okay. So that's, I don't have to care about that. That is just something that is okay. Right. But this is the cool stuff where you have multiple state machines. And if I'm not mistaken, it's 4. Yeah, it's 4. But we don't have to do that right now. So let's just start simple. So I think we can keep all of this more or less, except for we need 2 pins. So let's call it like this. And we also need the reset pin. Maybe we should start with that. So essentially, like if we open up the C code together, yeah, we want to wait for the reset to go high. And then we need these two signals. And then we also, or actually we can hard code that. Doesn't really matter. Set consecutive pin dirs. Right. So I guess we can start with these to be input or output. That is output, I guess. So maybe false. Just gonna look at the documentation. Okay. Is out. Yeah, okay. So false is input. So AD0 to AD15 is input for now. We will switch that later, but for now. Then get default config. I'm not really sure what that means. But okay. All right, that was the cool wrap and wrap target. I heard about that. That was really cool. And also the side set. Yeah, but let's not do that right now. But this way you could save a few instructions. That was really, really cool. Okay, so sm config set pins. Okay, what does that mean? Is that the output? Sets the set pins in a state machine configuration. Okay. So yeah, what do we want to do here? So again, eventually we want to write to these, but right now we want to read these and this one. So 16, 17, and 22 are for reading. So this. I mean, we can take all of them more or less. So let's just do like this. Ah, right, set pins. Now I remember. Now I remember. So these are the ones that we can write to with using the set instruction. Yeah. We don't really want to write those. So let's just start with writing to the logic analyzer, which is 26 and 27. Yeah, so these are the logic analyzer pins. Yep. Base and count. So 26 and 27. Let's put a comment. Yeah, the set pins. And then those are inputs. But yeah. Mm. Right. So I guess we want everything up to 22 to be input. And then 26 and 27 to be set pins. Yep, okay. Good. Then, yeah, let's just... So I guess we can just loop and do some stupid stuff. So let's just start by blinking really, really fast. Uh, I wonder if this will work. So we're just setting the value on the pins to 1, 2, 3, which should go to these pins, 26 and 27. So it's not called blink program, it's called cart program. And I changed some stuff here, right? PIO, state machine, offset. Oh. And then I'm gonna remove the, yeah, this stuff, because we don't want to interfere with the PIO. And this will start blinking just immediately. Okay, so let's try it. Let's see if it even builds, who knows. It does not. So I forgot to change something. Yeah, there we go. We don't need to do that. Program init. Right, this is ordinary C code, so we can just do a for loop here. And this is getting complicated now. Because we need to share pins between the CIC chip and the PIO. And I think the PIO gets exclusive access to the pin. Because if you remember, we have this cold reset pin, which the CIC chip needs, but actually it kinda doesn't. So let's just skip that for now. Or I don't know. No, it needs it. This got complicated. So the issue right now is that only the output is exclusive. They can always see the pins. Thank you. That is great information. That's perfect. So I guess we can still do this then for the inputs, which is up to 22 and including. Cool. Okay, let's try this then. So we expect to see the logic analyzer pins to toggle according to this pattern. Okay, builds. It's running. So let's see how it looks. Okay, it's dead. So did I forget to do something? I did this. And I guess I should not do that. Let's try again. Okay, nothing. So maybe I'm a little bit too greedy. Let's start simple. Let's start simple. So we need pin 25 and no 26 and 27. And let's just ignore that for now. Or maybe, oh, okay, wait a second, I forgot to do something. So, right. This is set 26, 27 as outputs. And here we set it so that we can use pins. That might work. Yeah, look at this. PIO, here we go. 20 nanoseconds, holy shit. Okay, let's increase our sample rate. How fast can we go? 8 nanoseconds. Okay, we're toggling so fast that my logic analyzer can't keep up. Awesome, 4 nanoseconds. Okay, so yeah, we have our first little program here, and it actually works. I think didn't actually save. Yeah, but this is awesome. This is definitely super fast, and I know you've done DVI and stuff. I don't doubt the capability, but this is cool for me to see. So I guess it's time to do something. Yeah, and we don't actually need to pull anything from the FIFO right now. We don't actually need to loop, or yeah, we will eventually need to loop. So let's implement the state machine. We will need some inputs. So this is for the LA1, LA2, and we need, yeah, for the rest, 4 and up to and including 22. And then here we configure the first 20, yeah, 0 up to and including 20. I guess it should be 23 here, to be honest. And then also we need 27 for the, no, what was it again? 25? That was 22, okay. So because this is the count, 0 is 1, and so on. So up to and including Gpio 22, our inputs. 26, 27 are outputs. These are the set pins. Off we go. So let's implement the state machine then. So where do we start? We're waiting for the cold reset. So how do we wait for a pin to go high in a good way? Sure, there is a instruction summary somewhere. Here we go. So I think we are waiting. Can we wait for multiple? Stall until some condition is met. Okay. Polarity, wait for a 1, wait for a 0. The source can be a GPIO, which it is in our case. But we can only wait for 1 GPIO. So how do we wait for 2? We could wait for, yeah, I don't know. Right, we don't need to mess with the input shift register just yet. So I guess let's just start with the simple one. So wait for the GPIO index 22, so the system reset. Okay, it's not affected by the state machine. Okay, so now the question is, how do I actually write this instruction? So wait polarity GPIO, and the GPIO should be 20. If ALEH is initially high, can you just wait for the L to go high? Oh, now I don't have the waveform here. Like I think initially everything is low until you turn on the console. And once you do that, things happen quite quickly. So H goes high, and then low goes high. So, but I guess we could wait for this one to go high, and then we wait for this one to go high. Like once, like this shouldn't go low before. Ah, okay, I see. Still, it seems like you could wait sequentially. Yeah, I think so. The problem though is that, yeah, we don't have to think about that right now, but if you turn up the console here or here, then yeah, I guess sequential waits will sort of mess up stuff. But let's start with this, just so we can get going. So Gpio num. So that was 22. So wait for N64 code reset. And at this point, we can set pins to 1. So we see it in the logic analyzer. And then, so this is that I actually turn on the system. And then we can wait for, let's see. Actually, let's see here. Okay. We can just start with this and see what happens. All right, I think I commented out a bit too much. Let's put stuff back in. Okay, it's fine. It should be fine. Okay. Okay, stuff is actually happening. That's cool. So what happens here in the beginning? This looks a little bit different. Or am I confused? Yeah, I mean, maybe we should start the state machine first when the system actually boots. Then that way we won't need to wait for this one as well. Yeah, let's do that. And we can do like this and like this. And then we can actually wait for H to go low. And then we can wait for L to go low as well. So let's do this stuff here. So once we are here, code reset is 1. N64 booted. Yeah, let's try again. Looks better. Yeah, look at this. So at this point, the function returns, and we call this returns, and we call this. We load the PIO, and immediately it goes to this state. I think I might be mixing up. Am I mixing up 1 and 0 perhaps? I don't know the bit order, to be honest. Maybe the bit order is reversed. That would explain why we go from 0 to 1, and it looks like this. Because that should be the 26, and this should be 27. Come on. Okay, there we go. But anyway, it looks like it's definitely doing something. And here we can calculate the latency as well. So here we have 30 nanoseconds between this one goes high. So did I actually do this correct? I'm waiting for high, and then I wait for low. Right. But it sounds a little bit high though, with 30 nanoseconds. Does that make sense? Or is it maybe because I'm sampling slow? I don't know. So I would expect this to be faster, to be honest. Let's try to sample it faster, just to test it. Okay, never mind. I don't know. It seems... How fast is 30 nanoseconds? 10 nanoseconds is 100 megahertz. So 25. All right, but anyway, we can see that stuff is actually working. So I guess it's time to do some interesting stuff. So how many instructions is this? This is quite a lot. So we're already, it's already feeling a little bit tight. But okay, we are here. So now we are basically Okay, so I guess it's time to sample some pins. So when we are here and ALE H has become 0, that is when we should sample the high part. So let's do that. So now we should use in, I think. Let me find the documentation again. So essentially, I want to sample 80 to 8015, put in input shift register. So how do you do that again? So maybe I can find some example that does that. Logic analyzer, that sounds good. There's no PIO. Okay. So when I do in pins, yeah. That is okay. So there's probably set in pins, right? So let's do that. Set in pins and the config. We want to start at 0 because we want 80 to 8016 as input. As right. And the instruction for in, can I limit that to only do 16 bits? I'm sure I can. I should just find the documentation for it. Here we go. Bit count. Yeah, exactly. So I want in source bit count. Okay, perfect. So in pins and then 16 bits. So at this point, I've sampled 80 up to and including 8015 and shifted that into the ISR. So how was it again? Is this now placed in the shift register or do I need to do something more? I think I need to do push, right? Push the contents of the ISR into the RX50. Yeah, and this is the cool thing that I don't need to do that now because I need to sample it once more here. So I guess I should do it like this. So at this point, push 32 bits of something like this. It's in the shift register, but not yet in the FIFO. Yeah, exactly. And this is what puts whatever is in the shift register into the FIFO. And then I think there was some auto push as well that would save me from calling this function. But we can start here and use auto push. So let's not use that just now. Okay. And then on the other side, I will need to pull. So I guess it's time to just kill this state machine because we don't want it anymore. And instead, we want to pull stuff from this. So how do you do that again? Let's look at some example code. Let's see. There we go. So okay, so let's start here. That will be interesting if this works. Ah, I got a reply from my friend about the chip. Let's see here. There you go. That was the high-speed capable microcontroller. It's also running RISC-V, which is kind of cool. Okay. All right. I forgot. We turned off the interrupt stuff. So maybe we should enable it again. Okay, I got stuff. Hey, look at this. This kind of looks almost, I mean, I don't know if it's right, but it's something. It is definitely something. So the address in the beginning is 0, and then we get stuff, but it doesn't look right. Because usually I think it's 256 bytes per request or something like that. But we're getting somewhere. This is cool. So again, just to show what I'm doing. Yeah. So after we start the CIC chip, we load and start the PIO stuff. And then we have a while loop where we are waiting for data from the PIO, and we print the result. And because we are printing it, we're probably messing up the timing a lot. So we shouldn't do that, but this works. That is pretty cool. So I think we're at the point where, you know, we're doing something. So now the question is, can we do something with this from C code? So we have the address, and now we need to load that data from somewhere. So ring buffer in RAM instead of printf. Yeah. that's good. Yeah, let's do that. Let's do that. Maybe this will be good enough. Oh, thanks. Let's just do it simple. Remove the null byte. Ah, damn it. No. I don't know. At least it will not block. Just do like this. Yeah, I messed up. I think I'm getting a little bit tired. Oh. How's it going? Okay, so just to do a recap of what's going on here. We have done a bunch of things. So first of all, we have imported the CIC C code implementation. We have made it work by implementing the Gpio stuff. So the CIC implementation works on the Raspberry Pi Pico. Then we tried to move that so that it runs on the second core, but that didn't work for some reason, and I still don't know why it doesn't work. But we put that aside and continued. So now we are doing the initial stuff that the CIC chip is doing, and we don't go into the sort of loop mode. But it's enough so that the whole request goes on. Like the N64 will perform reads from the address 0 and forward. So we implemented in C a C code implementation of a working FPGA implementation. So we ported that to C code. But because it's C code, it's slow. But we were able to verify that our logic works. So we're using 2 pins as a logic analyzer, and we can see that stuff is actually working the way it should. So now we are moving to the PIO stuff, which is sort of the main topic of this stream. So we imported some Hello World PIO and got it to blink, and that worked really great. And now we have improved on it so that we are waiting. We're basically re-implementing the state machine in a slightly different way. And we are, since we cannot print really, we are setting the logic analyzer pins from the PIO. And we can see here that it actually works. So this is the initial command or whatever request that happens. And we can see here on the logic analyzer pins that it is actually working. Dump the whole contents to stdio. Yeah, good point. I will do that. So the last thing that we did in the PIO is that we are actually sampling the pins, the AD0 up to AD15, putting them into this shift register. And once the shift register has 32 bits, we call push, which pushes the shift register's content into the FIFO. The FIFO is then being read from the C code down here. And what I'm doing now is I want to print the contents, but because printing is so slow, we see that the first request is correct, but this the ones afterwards are wrong. So right now we're implementing a faster way to print, which, yeah, it's just a few minutes and it should be done. But that's where we are right now. Okay, I was wondering, do both cores have access to all hardware at the same time? Could it be an arbitration problem? To be honest, I don't know. That could very much be it, but I also commented out everything from the core 0, so that core 1 is doing everything exclusively. Like the main function was basically start CIC in core 1 and nothing else, but it still didn't work. So at this point, I mean, it looks like an SDK issue, but I don't know. Because I don't know what I'm doing wrong. Because it's supposed to be as simple as just calling this function, more or less. So I don't know what's wrong. yeah, so now we want to get this ring buffer stuff to work. And it's midnight here in Sweden. And my brain is getting slightly tired, but it's okay. I'll continue for a while because this is really fun. So let's see here. We copy the ring buff content at the index with length. Oh, it's the other way around. We want to copy from data into the ring buffer. Stupid me. Okay, and then if the index plus length is beyond, that is also wrong. Should be size of. I feel like my IQ is like minus 200 right now. I'm doing really lots of stupid mistakes. But anyway, so if the index plus length is beyond the ring buffer size, then we know that we are going to wrap. So we want to write the null byte. We do put this. We set, and this is off by 1 error. I know. So let's do like this. And then we do put this, and we reset the index to 0. Okay, let's try again. Oh, typo. Okay. Time to try it out. Okay, it could be that the ring buffer doesn't fill up. So I guess we can. Let's just do like this. Okay, much more interesting, I think. But it also looks wrong. Interesting. Why doesn't it start counting from 0? So let's just do a review. Let's do a review. Okay, let's do every 5 then. Also, let's do like this. Okay, something is wrong in my code. I think it's the null stuff that might be wrong. Because we don't really want to write the null byte. But also this is concerning. Like the first word that we read should be at 0. Yeah, now stuff is weird. I don't know. Oh, I don't increment it. I'm really out of it now. I'm doing every single mistake that you can do, it feels. Because that explains why we get this one. Ditch this printf. Yeah. Okay, this looks much better, but it also looks kind of fucked up. But we get the 0 at least. But yeah, okay. Let's ditch the sprintf. So how do we do? We could make it into hex, I guess. How do you make a quick I to A? Because I had this issue a few days ago. To be honest, let me pull up that code. Push raw address, then printf when empty. Oh, why didn't I? Damn it! You probably meant that from the beginning, and I just didn't understand what you were saying. Let's just do this, right? We put the raw addresses on the ring buffer. Like, actually, just make it simpler. Like, do it like this, and we just have like this, and yeah, okay. And then we don't need to do mem copy. We can just say this one, and then you could actually do like this. Yeah, this is probably exactly what you meant, but I just didn't get you. I'm sorry. Yeah, and then here, instead of doing this, here we do for I. Okay, now we know you're not an owl type. Okay. Well, I mean, I did bike for 4 hours today, and I'm slightly tired in my body. We don't want that. We want this. Normally, I love being up in the night. Like, this is my prime hours. But I've been shifting back my sleeping schedule to accommodate work. It is what it is. Okay, I didn't get a print, so that could be that we have too many. The buffer is too deep, so let's do 32. Let's start with 10. Let's start with 10. Okay, here we go. So, does this make sense? It looks odd. Seems like we're missing a lot. But it looks way better than... so actually, let me think here. Maybe it's byte swap. But it should be the high part, because it's big endian. Maybe it's bit swapped. Maybe it's bit swapped. Because I'm not really sure the order of the bits. It could be like the bits should be flipped. Like if we just look at the trace here, this is not really how I remember it, but okay. So it's actually like every time you see the AL, E, L, and H toggling, we're sort of initiating a new transfer. And when read is toggling like this, bloop, 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 that is when the ROM or the cartridge is supposed to present new data. But usually this gets repeated many times before doing a new transaction. But in this case, it seems like it's actually performing a word-for-word transaction. Let me see if I have some old captures. Who knows what this is? No, not SVD. Okay, I don't have any VCD files left. I think I cleaned them up for some stupid reason. Okay, here I actually have a boot.vcd. That's cool. So thank you, past me. Here we have a single trace from the FPGA with all of the data bits active. So what we're looking at right now, and I'm really sorry for the small font. Let me see if I can make that bigger. I have lost the command because I know you can. I need to find that out. Because I remember. Yeah, here we go. There we go. Okay, so one more time. So now you can also read on the stream. So what we're looking at right now is a internal logic analyzer capture from my N64 flash card, which is an FPGA. So I can do stuff like this. So here we can see exactly what's happening during boot and the first few words that are being transferred. So in this case, we have these two signals. We have this pattern. And let's see here. Yeah, to be honest, this is interesting. So N64 address. I think this is right. So this is the 16-bit pins. There we get 1 0 0 0 and then 0 0 0 0. And we put these two together and we get this address. So I was actually wrong before. I thought I had misremembered. I thought that the address was supposed to be 0, but it's actually supposed to be 1 and then 7 zeros, like this. And then it increments 2, 4, and I believe this is the internal, this is like my internal register. So whenever we get a consecutive read toggle, I increment that value. You see here, this 44, that is something that I came up with. Like, it's not something that came from the N64. Like you see here, we have 4080, 6800. But anyway, here we have like the fact. This is true. And yeah, in this case, I have changed my ROM so that I present like a slow bus. So if you remember, we have this 8037, this one, and then 3040 versus 1240. So 12 means use these fast timings, but 30 means use slower timings. But yeah, now we have a reference, which is really good. So we want these values to match these values. So maybe we should start with the very first one. Like, why do we read 0 and not 1? So looking at the signals here, we have the high and low. So high happens there. So high and high is high. Yep. And then we get here where the H goes low. But then at the same time, the address changes. So the question is, when should I read? I'm a little bit confused now. Because if I read when this goes low, then it might be 0, it might be 1. It's a little bit scary. So maybe I should read it like, yeah, I don't like this. Because this is like multiple time steps. You see the clock here. We have one. Okay, it's only one clock cycle. So maybe I should have a NOP. I really don't like that. So we wait for high and low to go high. The last one to go high is the low one. Yeah. And then when this goes low, the high goes low. Yeah, maybe I should do like this instead. It could be that it's really sensitive. But at least I'm getting consistent results. But I don't understand why I'm not getting this one. I'm getting this. And then I'm replying with the 8037, 3040. This is coming from the cart. And then we get a new transfer with a new address. The address this time is 1040. But this one, I don't get it. It just doesn't show up. I mean, it could be that I haven't connected the correct pin, that I somehow messed up with the wiring. Yeah, maybe we should just assume that is what's happening, because that would sort of explain the pattern that we're seeing here. So let's say the OX1, let's say that this bit is incorrectly wired. Then these values make sense. We have 40, 44, 48. We have 40, 44, 48. Or actually, here, 48. So that actually works. So it sort of works. We're just missing one bit. That is probably because of my wiring, or that I'm doing like some off by one error somewhere. I don't know. Because I'm reading 16 bits. Yeah, that should be correct. The problem now is that we need to measure the latency that the rest of the system can reply with data, no matter where it comes from. So what if we do push and pull? Because let's use the debugging to measure this. So now from the C code, when this happens, we get the address, and then we should somehow reply with some sort of response. So how do you do that? So now we need to figure out how do you send stuff into the PIO. So put blocking, I guess. So let's just put OX1234, and then the state machine can continue. All right, it's actually a 32-bit word. So, so we can put a whole 32-bit word. And then we pull it, and then the pins should go back to 0. So this is not for, this is not going to be functional. It's just to see what is the latency we can get here. So let's do this. We do it like this. Okay, a few arguments. Put blocking. We need PIO SM. Okay. And then recapture. Okay, we see something. I don't really understand what this is about. Okay, it's just reset. Okay. Okay, so here we can measure the latency. So we are in the first state for only 10 nanoseconds. That is pretty damn fast. So that is that we get here. So from here to here, it's only 10 nanoseconds. So it's super fast to push stuff to the FIFO. That's good to know. But I don't think this is blocking, but it doesn't have to be blocking either. But when we pull, we're spending all of this time waiting for the C code to, we're waiting for the value to get here. And then we're waiting for this value to be put into the FIFO and then be consumed. And that takes 20 microseconds, which is, you know, it is what it is. So can we do better? So I think this is sort of a very important benchmark. So this limits how you can do stuff with this method. So I guess the proper method, I mean, in order to get down to as close to 0 as possible, we cannot use the SDK like this. We need to do it in assembly in a custom interrupt handler. This is POC as of now. You get more state machines. Yeah, you're right. You're right. You're right. We could, of course, implement. Yeah, we could implement the rest. Essentially, so I can just write some comments. So now read data from C code into output shift register. No, actually, yes. So now OSR will be data. Now we should out. So exactly when should we write the OSR to? Yeah, actually, we shouldn't do that just yet. So the fun thing, okay. Here's something that we could use. So at this point in time, we don't actually know if we're gonna read or write, but we can assume that we're gonna read. So we don't actually need to pull just yet. So let's wait and perform the next state. So we're essentially, let me bring up the FPGA code. Where was it? Here. So we are at this point right now, and we have pushed this to the C code, but we don't need a response just yet. So the C code can do whatever it wants. And right now we need to wait for the read signal to go high. So it's time for another wait. Wait for read to go high. And the read pin was something. 18. Okay. And when that is high, that means that we are, let's see here. Let's go to the start again. Okay, this is not exactly how I remember it. Because the read in this case is high all the time. And there it goes low. Wait a minute, there's a read active. Oh, okay. I was confused by my own code. It's supposed to go low. It's supposed to go low. Wait for N64 read being low. So when that happens, we can go back. That is when we present the 16 MSB first, I think, and then LSB. Yeah, exactly. So if you look at the hex dump of an N64 cartridge, it starts with this and then continues with this. So it is a big endian, but yeah, 16 bits at a time, big endian. That is how it works. So let's just do that. So at this point, now it's actually time to pull, and we just need to pull. No, let's pull all the 32 bits into the output shift register. And then can we write 16 bits to output shift register? So how does this work? Is this like out? And then instead of, yeah, and this time we're going to use pins again, but we need to change from input to output. So we need to change IO direction of audio pins to output, and which also implies later on that we need to change them back. So let's look at some example code. I2C, perfect. Out pin dears. Okay. How does that work? Set pin dears with mask. Okay. Let's read some documentation. There is no documentation. Or maybe this one. I don't really understand. Because if we need to switch the IO direction externally from C code, that's gonna suck. I'm probably missing something. Okay, so you can do this. Just need to open the window. 1 second. Okay, so we're gonna read more about set pin deers. This one. Here. Okay, so the out group is the pins affected by shifting out data from the output shift register using out pins or out pin deers up to 32 bits at a time. The set group is used with set pins and set pin deers. Right. So the set group, in our case, we use that for the logic analyzer, I think. The set pins, yep. But we don't want to use the set pins here because we are 0 indexed. So we can actually use the out pins. So instead of you doing that, we need to do out pin deers. And I guess there should be a mask for out pin deers. Let's look at the instruction for out. So what can out do? Destination bit count. Right, so in our case we want 16. Wait. I'm slightly confused still. I want to set 16. I want to set all of these 16 bits to output. So do I do like this? No. I mean, I want to change it on all of those pins, not just number 16 or number 0. Right, so we have the out base and out count. So what did we set it to? I probably need to set out pins. Right, we have set pins, in pins, and out pins. And how did that work again? Pin base, pin count. this is actually wrong. Shouldn't it be like this? No, okay, right, because the input pin, it wraps. But the output pins, they don't wrap. Okay, so now we have that out of the way. It still doesn't really explain how the pin tiers work. Right. But up to 32 bits at a time. Oh, now I think... No, I don't get it. Is the bit mask stored in the output shift register? Is that how it works? Okay, so I guess we need... I don't like this. Because that means that we need to fill the output shift register with stuff. So, which means that we need to pull twice. Yeah. So first we need to read so either I'm misunderstanding something or this is just how it works. So we need to read IO directions from the C code into the output shift register. Pull. And then we change the IO direction using the out pinders, and we're just gonna use the whole value. And then from the C code, instead of doing this, we're gonna put two values. The first one being yeah, does this make sense? Yeah. This will just increase latency a lot. So we wait for read. Once we get that, we read, we pull the direction, and we output the direction, and then we read the data, and we change the pin state. That's it. Just to get some more profiling, we can do this. When it goes from 2 to 3 to 0, we know the time difference. So yeah, let's try that. Oh, did some mistake. Okay, so I still don't really understand the out binders. Binders bit count. Okay, so I guess I need to do it for all 32, because otherwise the shift register will be all messed up, I think. Or actually, maybe it doesn't matter. We can just do the 16 LSB, because when we do pull, we will get the full data. No, let's do 32. I don't understand this well enough. So let's try this. And then out pins, we need to do 32, but because only some pins are outputs, it will be fine. But no, it will not be fine. Yeah, I'm really conflicted about this. And also this is not correct right now, but okay, stuff is happening. That's good. So in this case, we go from 0, 0 to 1, and then 2, and then eventually we go to 3 here, because, yeah, the read goes low. Okay, okay. So here we have some actual profiling data. So read goes low, and then we change to 3. So read goes low, that is this part. And then we pull the IO direction. We change the IO direction. We change the state to 3. We pull another one, and we output 16 bits. That takes a really long time. That doesn't make sense. No, it doesn't. Okay, because it goes low here. Okay, and that is actually super fast. It's only 20 nanoseconds for some reason. Okay, so this, okay, this looks actually pretty good. If this is correct. Yeah, 60 nano here. Yeah, if this is correct, then this is pretty cool. This might actually work now that I look at it. So you see these timings, it's 20 nanoseconds, it's super fast. Yeah, I mean, this looks suddenly feasible. I don't know really, the profiling that I got previously, that looked kind of bad, but something has changed here, so I'm not sure. Maybe it's the printing that messed up everything. So let's try to understand how this works again. So once we get the, it can be faster if needed. Yeah, good point. So, but I was just impressed by these timings. Like, again, we go from 0, 0 to 1, and then we go to 2. We wait for the read signal to go low. The time from here, this point, until this point, that is 60 nano. That is good. I mean, it's not perfect, but it should be definitely good enough to load the bootloader. Okay. Yeah, and like we saw yesterday, someone managed to overclock it to 420 megahertz, which is cool. But yeah, let's continue. Now I got energy again because this suddenly feels more feasible. I'm afraid we're gonna run out of instructions because this program is getting big. And I'm still, I believe this is correct, but I'm not sure if this is correct. Like maybe I should do this because otherwise there will be junk in the shift register. And yeah. Yeah, I don't know. Let's keep it like this and do it like this. And first we output the first 16 bits and then we wait. Let's see here. Then we go to wait for read. Wait for read high. Yeah, right. So we wait for read high. So now it's time to wait for some pins. And we don't want to wait for that one, but rather we want read to go high, not low. So it's pin 18. We want polarity to be 1. So when read goes high, that is this one. So we're waiting for this, and then it should go low again, and that is when we shift out the next one. So let's see how this works. So I'm outputting. Yeah. Okay, wait a second here. Right. So I'm just keeping it. I'm just keeping the bits set. And then, all right. So this is actually going to be hard because here we need an if statement. So either, so in this state, so what we're looking at here is sort of a special case where we're reading one word at a time. So during one transfer, we get one read signal that goes low and then high and low again. And then that transfer is done. However, you can also have multiple read toggles, I think up to 256. And if that happens, then in this case, in the FPGA case, we just keep looping. Oh, we keep looping it. We keep looping. Ah, maybe that is the trick. So we should keep looping here. However, but if one of these signals are high, then the request is done. But most often, it is the H signal that goes high first. So let's think a little bit here. So here we wait for it to go low. We pull. And this pindir stuff, we only need to do that the first time per transfer. Oh, this is a little bit complicated now. Because we need to reset the pindir state. Oh, this is, my head is starting to burn a little bit now. So essentially, at this point, we're waiting for N64 read to go low. And that is it's actually at that point where we should change the pin directions. I wish there was a way to wait for multiple GPIOs, but that also wouldn't really help. I mean, if we could wait for this, this, and this, like wait for those 3 GPIOs and then perform some sort of logic based on that. So maybe we should, I don't know. Okay, let's just do the naive thing and let's handle this initial state, initial thing. Okay, so we're here. Okay, I guess I can make like a command. So if N64 read goes high, I mean, it will go high anyway. It goes high here, but then it doesn't go low. This one goes high instead. So essentially, I guess here we should, instead of waiting, so this is like the wrap target, I guess. Or maybe not, because we want to go back to this. We need a label here. Yeah. So instead of using wait, I'm gonna have to actually read the GPIO state and do some logic. How do you do that? So essentially, at this point, if ALEH is high, like this, then we should return to the loop wrap target. So read so yeah, what do we have? We have We have jump. That is really cool. We have set as well. Yeah, I think that is the instruction we haven't really looked at yet. All right, that was the side set stuff. So I'm gonna write some pseudocode. So if LEH jump start else okay, does this make sense? So in this place, we want to read the state of this pin, and if it is set, we want to jump up here. But that is also not good because we need to reset the pin directions. And we need the pin directions from the C code. Which means that we need to signal the C code to send it to us. I don't know, can we? Just feels so strange. Maybe it's just not possible. Oh, branch on input pin. Check this out. That is cool. I did not know you could do that. That is cool. So you can do that. Okay. This will work. Jump condition. Jump pin only gives you one pin to branch on though. Yeah, that's good. But let's look at my pseudocode here if it makes sense. So just to recap, in case you missed it, in the initialization phase, we get read requests where one word is being read and then a new transfer begins and a second word is being read. But these are two separate transfers. Later on, you can get read requests where the read pin keeps toggling and the address gets incremented by the ROM or the cartridge. So in order to sort of handle these two cases, we cannot just simply wait for the read pin to keep toggling. We need to also check the LEH. So I wrote this little pseudocode. I put some labels here in the start and here. So this point is where we wait for read to go low. So we could check if the LEH goes high. With other words, we're waiting for this one. And if that is the case, we jump to cart start. So you could do that, right? We jump with the, was it the pin condition? I'm not sure about the syntax though. Maybe I can find some pseudocode or some example code. So that is the scratch register. But how do I refer to a pin? Do I have to write pin? Oh, here we have some. Jump pin good stop. But how does it know what pin is? Ah, here we go. Okay. I get it. Okay. So was it that? Yeah. And that pin was set to something. $17. Okay, now I get it. So now I can say jump pin, and then we're gonna go here. But I'm gonna be a little bit smarter and do this. And then we can do this. So that the first thing that happens in the program is that we pull the pin directions. That way we can reset the pin directions in this loop as well. So in the C code, we need to do this as the first thing. So we do it like this. Okay, so we start, we send zeros, we use the zeros, send them to the pin directions. The loop begins. But yeah, we're not really using the wrap target. Yeah, we are actually. So that's. We're actually not. Yeah, well, anyway, let's just go through it. So, pin directions, we do all of that stuff. Okay. Yeah, but this is not going to work either because there will be a delay. There will be a delay. How did you put stuff in the X and Y registers again? Set X. Can you use pins for set? Okay, so there's probably not a way to get a value or like a pin value into a scratch register X and Y, because can't really figure out how to implement this. So I guess I can only have one pin being assigned. The jump pin. Because I can only have one pin assigned. Otherwise, like ideally I would want something like this and have a different jump label, and then we can keep looping here. But can't do that. Yeah, I get the limitations. It is what it is. But now that you're here, like, can I sample a pin value to a register? You can also use a mixture of in and move to get bits into the scratch. Okay. So I was trying to figure out how to do that, and I didn't really understand. So okay, so there is a move instruction somehow. Right, I missed that. Okay, now we're back on track. So let's do that. It's gonna be a little bit wasteful, but let's do that. So move, what's the syntax? Destination and source. Okay, and I guess something like this, and then jump to this one. How was the jump? Right, if it's here. Let me think. Yeah, if x is high, we want to keep looping, and then this is not needed anymore. There is no move for a single pins. Oh, okay, I see. But that's perhaps not the problem. You have to fiddle around with the ISR and OSR. Okay, so can I change the OSR from the PIO code? Like, can I? Because I was doing something perhaps kind of stupid, where I want to do the pindirs, but I need to have values in the OSR, so I pull it. You can move OSR. Okay, that's cool. So yeah. Okay, don't worry about it. Okay, so let me try. So instead of doing this, move OSR pins. Okay. But okay, so what does this actually should I have? What? I see. Okay. Move OSR. Yeah, I see. I'm just my brain is not working really, so let's do like this. Okay, so let me just try to parse and understand. We're taking all of the pins, all of the 32 pins, or 16 pins, right? Because this is move, so these are the in pins, right? The ones that I set up here. So the in pins are being placed in the OSR, and then we are outputting from 0 index to 16. But where does it go? Move OSR pins out null. So I'm kind of confused about this one. What does this actually do? It consumes 16 bits. Oh, it's in order to get the index 17, or is that correct? Dump 16 bits of OSR content. Okay, I get it. Yeah. And this is read bit 17, essentially, or yeah, I mean, because now the out, when we output 1 bit, I get it. Now I get it. Cool. This is really cool. I would not have been able to write this myself. But now this has been a learning experience. Learned a lot today. Gpio 16. Oh yeah, because it says 0 indexed. No, don't worry about it. Let me just double check. It might be. It is actually 18. So let's do 18 bits instead. Or actually, do I need to? No, actually, we're consuming 18, so we get 0 up to 17 are thrown away, and bit or GPIO 18 is left in the out OSR. We consume 1 bit, and then we jump somewhere if it is set. And if it is set, we keep looping. Otherwise, we don't need this anymore. And then maybe we don't need to do this weird stuff. So I was trying to solve the problem of setting the pin directions, and I ended up doing something strange perhaps, where I am writing a 32-bit value with the bit mask, and I pull it, and then I out pindirs 32. But maybe can I guess it's the encoding issue. There's not room for 32 bits. So I guess I have to do it like this. Because you do like, or can pins actually be, we should have added a move pindirs axis. Okay, so this is like a known thing. Is this how I should do it? Because I guess I cannot do move OSR and then a 32-bit value here. Because move, yeah, encoding space. Yeah, source. Oh, you can do move OSR, not null. Oh, that is clever. That is clever. Let's keep that in mind. Move OSR not null. The problem with that is that it kind of changes everything. So later on when I want to set it to null, I mess up my logic analyzer pins, but that will not be a problem later on. So let's just keep that in mind. Yeah, that was a really good trick. I will remember that. Okay, so back again. So reading the pin, and if it is set, we go back here and we do the pin layer stuff. And actually for zeros, yeah, for zeros we can actually use the trick. So let's do that. But in this case we want to set it to null. So that's gonna mess up, and it doesn't really matter. It doesn't really matter. Let's do this. Yeah. Set pin 0. And we do all the stuff. Right, if it's set, we keep looping, and once it goes low or this happens, yeah, we can continue. Now this gets a little bit more complicated. I guess I'm actually gonna have to use your suggestion because yeah, this will just not work. We're gonna have to do it like this. Now this might be a problem. Oh, maybe I can just pull 16. Can I do that? No, okay, so pull always pulls a 32-bit. Okay. So the problem that I'm facing right now is that because of the 16-bit, yeah, the bus is 16 bits, we need to pull once, but output twice. So I guess I can do that by waiting. Yeah, okay, I can do that. By copying code. Still, I believe we're gonna run out of instructions. It just feels like it's gonna happen any second. Write 16 bits. And then wait for it to go high. Is there any reason not to put it in two FIFO entries? No reason. Oh, I get what you mean. Okay, so I basically push it twice. Like this. It just like feels wasteful because I know it's like 32 bits beneath. But yeah. That totally makes sense. Now, because I'm so scared about latency, I'm thinking like, oh, I just want to do this as few times as possible and so on. But yeah, this might work. Yeah, and here we waited for it to go high and then goes low. Wait, this is wrong now. I think I need to proofread this now once again. So here we wait for L to go low and H to go low. So at this point we are here. So we are exactly at this point. We are waiting now. Yeah, because now we have the address, we push it. And now we wait for read to go low. And that happens here. So now we are here. We change the pin directions and maybe this should be in a different order. Right. So we pull 16 or 32 bits, but we only use, I guess we can do like this. Yeah, so at this point, we should go there. I believe this might be correct. So this loop is the interesting part. Okay. So if the transfer is done, we go back to the start where we reset the pin directions as well. We do the check for one Gpio and jump thing for LEH. So that is in case we are done. This is for debugging. Pull. Okay, I think it's we're ready to try it. Yeah. But I'm not really sure how I'm gonna debug this properly. Okay. Could be that nothing works now. Okay, something happens. Okay, this might be that we're blocking for some printf. But yeah, it looks like something is happening. So I guess we can try to actually load some actual ROM data. The problem is that because I have a limited logic analyzer and all of that, it's kind of hard to know if the correct data is being output at the correct time. I guess we can. I guess at this point I can change the sniffer, the logic analyzer, to sniff the two LSBs on this one. So I'm gonna do this. I'm gonna rewire it so that these two sniff the 80 0 and 81. Yeah, let's try that. Okay. So it's connected now to the two LSBs, so 80 and 81. So unfortunately, the address will always be 0 because of the 32-bit nature of the system. But we could do something like this. And hopefully we will see something interesting. Okay, it's all zeros, which is bad. Because, yeah, it should have outputted those values. Trying to figure out what's wrong now, because previously we saw that the states seem to change properly. Could it be that there is some junk? Oh, actually, this is wrong. Let's try again. Okay, still zeros. Yeah, I don't know really. We're pulling and we're outputting directly after, because the OSR should contain data at this point. Yeah, oh, right. It's going to be a problem later on as well, because this one needs to know that we want data. So I guess I can encode that in the LSB. I have 2 bits. So essentially, I could output, yeah, whenever I need data. Yeah. So after we send, like here we send the address, and then later on we can send that we need data. I wonder how many instructions this is. It feels like we were close. "24 instructions. So we have 8 instructions left. We are pretty damn close. At least it feels that way. So at this point, I'm not really sure why this doesn't work. Actually, I think we can get rid of this one too. Okay. I'm just gonna just put a lot of FFFF, see if that changes anything. Okay, I don't think I'm getting anywhere now. So just proofreading. We set pin directions to null. Everything is input. Yeah, let's remove the debug stuff. We wait for both to go high. We wait for H to go low. We sample the pins into the ISR. We wait for L to go low. We sample the pins again. Now we have 32 bits of data, but they are in the wrong order, I think. But it doesn't matter. Now we push the address that we have, which is being consumed here. Okay. So now the C code knows the address. So it just immediately sends some stuff, which is in the FIFO. At this point, yeah, let's double check this pin. So at this state, L and H should be low. So having this jump should be safe, because we're here. I have a feeling this might be off by 1 or something. Oh, I think the jump is wrong. I forgot this. I forgot the condition. Should I have a comma here? Like so? Okay. No comma. Okay, I can do this, I guess. Oh yeah, thanks. Okay, it's building. Interesting. Hey, check this out. This is correct, because okay, this looks a little bit junk though, but other than this part, we're getting somewhere. So let's put this back to 0x01, like this, and 02. So this way we should be able to see the difference between the two reads. So let's give it a try. Okay. Yeah, this looks like 1 and 2. But then it dies. So it died for some reason. Not really wait a minute. this shouldn't happen. This should happen at this time. So something is clearly wrong. Let's move this over here and move this way. So read goes low, and we do this. But we shouldn't do this on this second thing until this happens. So yeah, we're definitely one step further on the right track. So pull out. Oh, I think I removed one important line. I should wait for read to go high, because read will always go high. It is just that it might go low, but it will always go high. And read was pin 18. Let me just double check. Yes. Okay, one more time. What? Okay, it got stuck again. Looks the same. That's weird. I don't understand. Waiting for positive polarity of N64 read. Because here we have waited for it to go low. Oh, right, because at this point, we don't have any inputs, which means that we can take this, put that here. No, here. Or like this. So one more time. We are pulling and writing the pins, and then immediately after we're changing the pin directions. No, that's no good. That's no good. Damn it. That will not work, because we need to keep... Can you shift stuff into the OSR? I guess not. Thanks for the follow. So at this point, we don't want to do this. We don't want to change all of the pins to input, but we need the N64 read to be... Oh, I got an idea. Let's do this trick so that only the 80 pins become output. And then we don't need this. Okay, let's read the code one more time. So we have waited for read to become low. It's not all pins. Oh, okay. Oh, right. It's only the out pins that I define here, right? The shift count is how much data is taken from the OSR, not how many pins are affected. Okay. Okay. I should not do that then. So okay, so let's try again then. So is my understanding correct that Or we see here. Yeah, we first need to wait for read to go high, because otherwise this logic won't work, because the read will still be low. Yeah, so we need to wait, was it 18? Yeah, to go high. Now we have that there already. So we write the pins, we wait. So at this point, even if we have this, I should be able to read this Gpio. And then we jump up here and everything should work. Let's try again. Same issue. But no, it looks different this time. It looks a lot different this time. But I'm not really sure what's happening. But yeah, this is correct. Okay, have a look at this now. So this is the initial transfer. This is the first time read goes low. And this is where we send OX1. Then read toggles and we send OX2. And then at this point, the N64 will read the state of the pins. And then sometime later, ALE H and L goes high. And a new transfer begins. But this time it goes way faster, because we fed it with junk. So this time let's do the interesting thing. So now we should actually feed it with 80, 37, and 40, which is the data bus speed configuration. So the reason why the timing is a lot different here, super fast, is because we actually told it to be super fast. Because 0, like, you configure it with a time, like in nanoseconds, or not really nanoseconds, but in some cycle multiple or something like that. So when you send zeros, you're basically telling it to go super fast. But now let's tell it the proper thing. Oh, damn it, I forgot to start. $50 nanoseconds. That still sounds kind of low, but it looks way more. Well, this looked kind of weird. Wait a minute. So yeah, first we send this one, then we send this one. If we compare here with the FPGA implementation, yeah, that is what I sent. And I think the bit order is even correct. Damn it, it feels like we're so close now. So I wonder what is going wrong now. Because these speeds, they indicate that we have configured the bus to go like way faster than it should. It should be like 300 nano and not 50. Yeah, but I guess just for testing, we can set it to FFFF. Actually, I changed it from blocking to not blocking, but it should be blocking, I think. Yeah, the problem is later on we won't really know if we have to write more bytes or not. Strange. So now I changed the no, okay, I didn't actually change anything. Now I changed the data to be FFFF. The purpose is so that the timings are slower. And look at this, it actually works. So the change I did now was I changed the timing, or like the initial timing parameters, to be just FFFFF, which means that the bus will be configured so that the read timings are much slower. So in this case we have, what is it, 3.7 microseconds, which is like in eternity. And as you can see, the Raspberry Pi has no problem to accommodate those request speeds. Byte order, bit order. Yeah, I'm starting to think that there might be something like that, because yeah, that's why I tested with all of the bits set to 1. Because then yeah, we get like the longest. So yeah, it might be something like that. So I don't know if the shift register is like reversed. But I guess, I mean, we did the OX01 and OX02 test, and that seemed to work. So the bit order seems to be correct. So in this case, the first one should be OX01, which is, this is bit 0 and this is bit 2. And as you can see, bit 0 and bit 1. So the bit order seems to be correct. But these timings are not fast enough, or slow enough, I mean. Maybe it takes first highest bits from FIFO and you're feeling just lower half. My understanding is that when I call pull, it reads 32-bit, like one entry of the FIFO. But it could be that I have junk in my shift register so that it sort of, I don't know, doesn't replace everything or something. But I also believe that pull, okay, FFFF gives really slow timings, so probably not. But if everything is always FFFF, then, you know, maybe I should try this. Because previously I had 32 bits of FFFF. So it could be the 16-bit stuff that messes up stuff. Maybe. So actually, maybe I should use 32 just to be safe. Okay, this looks just like before. Try sending it to FFFF and see if it behaves. Yeah, that is what I did just now. And it looks at least very similar. We have the 3.71 and then we have 10.27. And then here we have 13.99. Yeah. And I believe that this is more or less what we had before with the 32 bits of FFFF. But I'm gonna try something else. Okay, I'm actually using 32 bits. I'm actually using 32 bits. Then I don't really know. This one I shouldn't do. Maybe that was confusing me before. Yeah. This is an old debug instruction. So yeah, now we are using the proper configuration. So let's do a test. RMS little endian, MIPS is big endian. Oh. I mean, I know, but I didn't think about that. Yeah. Okay, so let's, but wait a minute. Should we byte swap these? Like so. Yeah, let's try that. Okay, this looks different. I'm not sure if it's right. We have 1.05, and 3.85. What is it supposed to be? It's supposed to be way faster. So, I don't know. It's different, but yeah. Because the 01 test that we did before. No, actually, okay. So what we did before, we did like this and like that. And I have the logic analyzer hooked up to AD0 and AD1. And they indeed were 1 and 2. So the byte order seems to be correct. Like this 7, it's all ones. And then the next one is 0. And we could see that we had both of these being 1 and then following one being 0. So yeah, I'm starting to think that this is actually correct. And that bits are being stored in the right order and that the bytes are in the right order as well. But because I think, if I remember correctly, this is in big endian as well. So my 16-bit register had this value, where the LSB is AD0, more or less. So yeah, I can't explain why we got those weird timings, because it's, I mean, we can confirm that we can affect the timings by changing it to FFFF. And if we byte swap, we also change it. But if we keep it at this, we get kind of fast timings, like way too fast. 50 nanoseconds. One more time. Yeah, 50 nanoseconds. I have no idea what's going on here. I think it went out of sync. Yeah, okay. It almost works, but doesn't really work. It could also be that I have hooked up some wire in an incorrect direction so that this gets encoded as something else because I connected something incorrectly. That is definitely a possibility. So to be honest, at this point, I think we've done a lot of cool progress today. And I feel that my brain is reaching its melting point. But it's been a lot of fun, and it's been really awesome to have Luke here, who's been helping out a lot. Thanks a lot for all the feedback. I've learned so much today, and it's been a lot of fun. And I really hope to, boot some homebrew. That would be so cool. But maybe that will have to wait until I get the PCB with the proper this PCB, because this will be connected correctly and there won't be, I mean, it's not a perfect board, but it won't have as much signal integrity issues as my flying wires and all of that. But I think it was still worth connecting it. Try shifting single bit around the byte borders. Oh. Hope to catch another stream of yours sometime. Yeah, you're welcome. We're very nice to have you here. Thanks a lot. But yeah, I don't know. Oh, okay, I get what you mean. Shifting a single bit around byte borders. But yeah, to be honest, that's a really good suggestion. But yeah, my brain is melting. So I'm gonna end it here. But thanks a lot, and it's been a lot of fun. So see you next time.